Chapter 9, Climate Regions and Climate Change. Section 9.3, Natural Variability of the Earth's Climate. So what we're going to learn in this section is that the Earth's climate has varied considerably over time. In fact, during most of the Earth's history, global temperatures were some 8 to 15 degrees Celsius warmer than today, creating tropical conditions that extended into the middle latitudes and in some cases into the high latitudes. About 2.5 billion to 500 million years ago, there were probably 4 events where ice sheets covered most of the Earth's surface. These events are known as snowball Earth events. During the last 500 million years of climatic history, warmer conditions were broken by glacial periods. And so what I'm getting at is that for the most part, over the last 500 million years of Earth's climate history, warmer than average temperatures relative to today existed. There were these glacial periods. One occurred from about 460 to 430 million years ago. Another from about 360 to 260 million years ago. And then the last one started approximately about 2.6 million years ago. Antarctica, in fact, began freezing over about 14 million years ago. So here we see a relative measure of whether the planet was in a hot phase or a cold phase based on oxygen-18 isotope measurements from sea cores. These glacial periods are located on this graph on the bottom. Now, the timing of when these occur, it's relative. So I did say, the last glacial started about 2.6 million years ago, but depending upon where you suggest cooling begins and warming begins, it's relative. So we can see that there were hot periods about 500 million years ago, about 380 million years ago, another hot peak at about 270, and then the last hot peak was about 90 million years ago, and then temperatures started declining. So let's focus now on the last glacial period, and we're going to suggest it started about 2.6 million years ago, and that last glacial period is known as the Pleistocene, or more commonly the Ice Age. Now, of course, there were several different ice ages during Earth's climatic history, but Ice Age is used commonly to describe the last one. During the Pleistocene, which occurred from 2.6 million years ago to the beginning of the Holocene, about 14,000 BP, glacial ice sheets covered much of North America, Europe, and Asia for extended periods of time. In fact, in North America, glacial ice sheets covered all of Canada and extended into the southern United States during the last glacial period, or glacial advance. And remember, during this Pleistocene Ice Age, it wasn't just constant cold. It was warm periods and then cold periods. And the cold periods tend to last 8 to 10 times longer than the warm periods. During the coldest periods of the Ice Age, average global temperatures were probably 6 to 7 degrees Celsius colder than they are today. So that's an estimate. There was some research recently published with some more accurate numbers, but I can't remember what those numbers were. Pretty sure they've been updated in the textbook. Warming of the Earth and glacial retreat began about 14 thousand years ago, or about 12,000 BC. So we call this period of warming that extends to today the Holocene epoch. So here is a reconstruction of past global temperatures based on the ice core retrieved from Vostok. So the top graph shows us relative temperature change. So we can see that over the last 450,000 years, there was a warm period about 420, 425, another warm period at about 350, another warm period at about 250, an extremely warm period about 130, and then beginning about 14,000 years ago, we get the last warming occurring on our planet. This next graph shows relative temperature change during the Holocene back to about 12,000 years before present. And what's measured here is temperature anomaly, so how temperatures varied relative to some norm. And the norm they're using here is mid 20th century temperatures. So around the middle of 1950, a certain number of years either side of that. So we can see that we quickly came out of colder temperatures. They warmed up, and by about 10,000 years ago, temperatures were equivalent to this mid 20th century average. There was a slight dip, and then we get a warm period, relatively from about 8,000 to about 4,000 years before present, and scientists refer to this period as the climatic optimum. From after the climatic optimum, there's essentially a decrease in temperature until we get some of the lowest temperatures just a couple hundred years ago during a period known as the Little Ice Age. Also graphed on here is the average temperature relative to this 1950 measure for 2004. Today would be approximately about 1 degree. So high, it would be about 1 degree, so much higher than the 2004 value. So it's obvious from that graph that during the Holocene, the Earth experienced a number of climatic fluctuations. As I said, between 7,000 and 3,000 BC, average global temperatures reached their maximum level during the Holocene. Some 0.3 to 0.6 degrees Celsius warmer than the 1961 to 1990 average. Don't get confused by that. The climatologists do this all the time. They pick a standard and then they compare temperatures relative to that standard. And in the graph, the standard is actually mid 20th century. So climatologists call this period the climatic optimum. This climatic optimum, the dates vary a little bit. On the graph, it almost looks like it was between 6,000 and 2,000 BC, but somewhere in that range, or 7,000 to 3,000 BC. After this period, global temperatures experienced a steady cooling trend. Now, temperatures didn't just continually drop after the climatic optimum. There was another warming period, or warm period, that lasted about 300-400 years, known as the medieval warm period, or the Little Climatic Optimum. And it dates somewhere around 900 to 1200 AD. And then between 1550 and 1850 AD, we get some of the coldest temperatures since the beginning of the Holocene, and scientists call this period the Little Ice Age. During the Little Ice Age, the average annual temperature of the Northern Hemisphere was about 1 degree Celsius lower than today. So how cold was that? It was cold enough that the Thames River in England would freeze over, and you could skate on it. That can't happen today. Here we have another reconstructed record. This one going back 2,000 years. So there we can see that medieval warm period between 900 and 1200 AD. And as I said, it's kind of tricky trying to determine when it starts and when it ends. All of those lines represent different sort of records, and they're superimposed in each other. And normally what climatologists would do would be to run an average through that to get a better indication of what was going on. So we can see the medieval warm period. There's the Little Ice Age. Different records say different things about how cold it got. So let's now look at a close-up of the record since 1880. Oh, one last comment related to this reconstruction. The average that everything's being compared to, the temperature anomaly, looks like about 1961 to 1990. Okay, the next figure is really interesting. It's based on instrumental data, so it's high quality. And what is shown on this graph are global annual mean temperatures. So this is an average of all the recording stations on the planet for a 1-year period for years going going from 1880 to 2019. And the trend is obvious on this graph. Temperatures are increasing. In fact, the last 5 years of this record are each the warmest years this century and possibly since the little climatic optimum. One particular year stands out, and that's 2016. It was the warmest year globally in 1,200 years of Earth history. 2016 was more than 1.4 degrees Celsius warmer than pre-20th century temperatures. And we're talking about the period from about 1851 to 1990 as pre-20th century. So there's the yearly measurements. Notice that there's about 0.2 degrees Celsius variation occurring from year to year. That's the internal variation within the climate system. Much of that variation is created from a cycle that occurs in the Pacific Ocean. The cycle that produces El Nino and La Nina is responsible for those variations. With an El Nino, more heat energy goes into the atmosphere rather than the ocean, and that causes atmospheric temperatures to blip upwards. When a La Nina occurs, more energy goes into the ocean and less into the atmosphere, resulting in a slight downward trend. Temperatures began increasing globally probably about, at the beginning of the 20th century. They reached a peak in about 1942, 43, and then declined a bit and then leveled off. That period of sort of no temperature change between roughly 1943, 1944 to the mid-70s, we know what caused that. Two factors. One, us loading the atmosphere with reflecting dust particles that limited the amount of shortwave coming in, and a much larger cycle in the Pacific Ocean known as the Pacific Decadal Oscillation. When starting in 1975, the warming returned. The PDO went into a phase where it was releasing more heat energy into the atmosphere than the ocean. Works very similar to the El Nino La Nina cycle. And we reached a maximum in terms of how much, or the concentration of aerosols in the atmosphere. So they were no longer holding back global warming, and global warming proceeded to occur, rising each year starting in 1975. And as you can see, it seems to be accelerating in the last decade. And if you look at in particular the last 5 years, the last year being 2019, those 5 years are warmer than anything in that period. And as I said, probably anything back to about 1,200 years ago. So this graph shows us how La Nina and El Nino seem to influence the variation in the temperature record. So when we have El Nino events, there's a sharp, or a slight blip increase. La Nina causes it to drop, but the overall trend since the mid 1970s is increasing temperatures. So many scientists believe the warmer temperatures of the 20th century are being caused by human enhancement of the greenhouse effect. Since the beginning of the Industrial Revolution, we have been increasing the concentration of carbon dioxide, methane, and nitrous oxide in the atmosphere. This is enhancing a natural process called the greenhouse effect, and it's caused the Earth to be roughly about 1.2, 1.3 degrees warmer now than before those gases were in the atmosphere. If we continue to emit greenhouse gases, and it looks like we're going to do that for several more decades before we get our act together, temperatures may rise an additional 1 to 3 degrees Celsius by the end of 2100. As I said, 2016 was one of the warmest years in the at least last century, and this map shows us where temperatures were warmer relative to 1981 to 2010 base period. And we can see that much of the planet was experiencing temperatures warmer than that 30-year period that was not too long ago. We'll come back to this in Chapter 10 and learn more about climate change as it's being caused by human emission of greenhouse gases. The last thing I want to talk about in this lecture is just how do we reconstruct past climates. The most obvious method would be just to use meteorological instrument records, but these records only go back so far. Maybe while we have records that go back to about 1850, they don't get good coverage of the planet and good methods of recording the data till about 1940, 1950. So instrumental records are important. Prior or before these instrumental records, we use a lot of other types of evidence to reconstruct past climate. One form of reconstruction can use just descriptive accounts of the weather. Sometime around 900 AD, the Nile River froze during December or January. Well, that's pretty obvious evidence that temperatures were much colder than they are today. Or if you go to Europe and look at some of the paintings in the museums, paintings from the Little Ice Age, you'll see glaciers that are further down valleys than they are today, indicating that temperatures were colder. Or in Japan, they kept accurate records of when cherry blossom would occur. And it's occurring earlier and earlier and earlier. Or in the Okanagan Valley, if you talk to any farmers that have been around for a long time, they'll tell you, for example, descriptive account that their growing season is increased by about 2 weeks, indicating warmer temperatures. Or another good descriptive account of weather change in the Okanagan is Lake Okanagan used to freeze. It would freeze to such an extent where you could drive a car across the lake from Kelowna to Penticton. Well, that really hasn't occurred in the last few decades. It was a more common occurrence in the beginning of the 20th century. It doesn't occur anymore. Things have warmed up too much. The last type of evidence that's out there to reconstruct past climate is some kind of physical or biological data that exists as fossil evidence. And what you're looking at is something that responds to climate in a proxy sort of way, so it's called proxy data, and therefore records the fluctuations of past weather on our planet. And one classic example of that is tree rings. So depending upon what is the limiting factor, whether it's temperature or moisture, you can determine from that how those two climate variables varied over time. So if it's temperature, the tree rings will be narrow, indicating colder temperatures. If the temperatures warm up, the tree rings get wider. That's the end of this section.